Hello guys, we'll be looking into a definite set of population of information which can be loosely translated as a data set. So this data set just comprises of a single independent variable. Now our intent was, supposing a new member is added to this data set, what would be the probability of the value assumed by this new member? So the data set that we have been considering comprises of lattice parameters of different alloys. And these lattice parameters of the different alloy, they constitute a population. And this population we represented on a scale, and thereby we were able to have a distribution of population. So this population, which comprises of the different lattice parameters assumed by a set of alloys, we were able to represent it in a scale, and this ultimately led us to the population distribution. And when we introduced bins are nothing but they are rather characterized by a range of the values of lattice parameters. When you introduce your bin, and then you rather categorize these population distribution and you arrange it in such a way that the alloys, they lay one over the other. When you do such sequence of operation, what you would end up having is an histogram representation of this population distribution. So you start off with a combination, a population of independent variables. You represent it on a scale, and when you represent it on a scale, again the scale should be relevant to, or it should be appropriately devised to encompass all the population. And when you represent it on a scale, you end up having a population distribution. Now once you have a population distribution, there are numerous ways of handling it. So what we did is we introduced a bin, and this bin comprises of, or it dictates the range of the values of the lattice parameters. And once you introduce this bin, when your population lie within this range, you put them all together in this bin and you arrange it in such a way that they lay one over the other. That would lead us to histogram. And from this histogram, we are able to fit a curve over it. And this curve, we represented it as the distribution curve. Again, so far, all that we have is just one independent variable. And this independent variable, the population distribution of this independent variable, we were able to arrive at this distribution curve. And this curve is not in itself a function, so we wanted to describe this curve. And when we introduced, or when we replaced the population density, the population with the probability, then we were able to arrive at what we refer to as the PDF, the probability density function. So this is a function of x, and from this we were able to also arrive at the cumulative density function. So from a single, or from a population of a single independent variables, now we are able to describe the probability density function and the cumulative density function. Both of these will enable us to calculate the probability of a new member assuming a definite value. So in case of probability density function, you have to have the definite value and create rather a range, and by introducing that range and estimating the area under this probability density function, which is nothing but the curve, you will be able to estimate the probability of the new member assuming this definite value. Now the cumulative density function will enable us to rather estimate the cumulative probability, that is rather ranging from the minimal to the probability through the desired value. And all this from probability you will be able to estimate from the entire probability, you will be able to estimate from the cumulative density function. And basically the way you would handle both these functions, you would either end up with a specific value or a set or a function. That's the reason why for a generalized description they are referred to as the probability density function and the cumulative density functions. So we have seen rather three most commonly used distribution functions, or most commonly observed distribution functions. So one is the normal distribution, and the other is exponential distribution function, the other is the gamma distribution function. Now when you want to qualitatively describe it, a gamma distribution function or the Gaussian distribution function would look something like this. Exponential function would look something like this, and a gamma distribution function would look something like this. Now once you would draw this plot, it becomes rather straightforward or relatively easy for us to bring about these axes. So the key difference here is, in case of the normal distribution function, what you essentially have is the maximum population is rather concentrated on the average value. So the characteristic feature of the normal distribution function, quantitatively speaking, is rather the highest population you would observe in the average value. And as you move away from the average, you would observe that this population gradually decreases. The probability gradually decreases. Since we are talking in terms of the PDF, the probability of the member assuming the value away from the average gradually decreases. Now in case of exponential function, what you observe is that the probability is highest in the lowest value range. And as you move away from this lowest value, the minimal most value, the probability progressively it decreases. Now in case of gamma, the peak or the most populated region is it is not concentrated at the average, it is not concentrated at the minima, it lies somewhere in between, and we saw the reason why we refer to this as the gamma function. And as you move away from this peak, again the probability of the member assuming the value gradually decreases. So this is the probability function and this is the population distribution. So this is the, if you consider in our case this x, here is the lattice parameter that of the difference alloys that we have considered. Now what we have essentially seen is we have essentially developed the probability density function, separate probability density functions for all these three different distributions. Now when you focus on the normal distribution, the way we characterized this normal distribution was using mean and variance. So if you could recollect, the way the mean is calculated is rather straightforward. We have measured rather, so supposing if our data set, the population, the total entire population comprises of n different members, then the mean, which is represented by mu, is rather calculated by the summation of the lattice parameter assumed by the n members. So we are considering the lattice parameter assumed by the n members, summing it all up, dividing it by the entire population. So this is what we refer to as the population mean. Now it is also possible for us to describe the variance. So the variance, the population or rather the mean describes where your function is centered, and the variance it rather describes the spread of your function. So this variance sigma square is rather described by the difference between the individual. So you have individual lattice parameter and you have a mean. So we want to know how spread is the observation from that of the mean. So you are considering the difference between the individual lattice parameter from that of the mean, squaring it all up, and again you are considering just not for one member but all the member ranging from 1 to n, and you are taking the ratio with respect to the entire population. So this will give us the feature that characterizes the normal distribution, that is mean and the variance. Now these have specific name associated with them. These are referred to as the population mean and population variance because this population is rather huge. When you consider the number of members in this population is rather huge, so therefore we refer to it as the population mean and the population variance. However, in real studies or in the real life situation, what we observe is what we have is just a sample of this entire population. What we have is just a sample of the entire population. And whatever studies we are making, so suppose if your sample is, say for instance 100,000 data sets, so for instance if you are considering alloys, and so far you have the data set of 50 alloys, which is practically possible, but the possibility, when you consider the possibility, it is possible for us to tweak the alloy composition in such a way that we can have say 1000 alloys. But for our convenience, we have just tweaked the experiment in such a way that we have 50 alloys. So from the possibility of having 1000 alloys, what we are having is just 50 alloys. So essentially we have a sample of the entire population that is possible. So when you have the sample of the entire population that is possible, then the mean and the variance that we are estimating are based on this sample. So the mean and the variance, they depend on the size of the population, and when you have a population that is entirely possible, all the possible populations are being considered, all the possible members are being included in the population, then the mean and the variance that you estimate are referred to as the population mean and the variance. However, often in real life what we have is a sample of the population, and when you estimate, we often what we have, unless otherwise we have a huge number of data, we often refer to it as a sample, and whatever mean and variance we estimate from the sample, we refer to it as the estimated mean and the estimated variance. So the population mean and population variance translates to estimated mean and estimated variance when the size of the population is reduced, and for all practical intents and purposes, what we essentially are dealing with is estimated mean and the estimated variance. Now the expression for the estimated mean remains the same. So the estimated mean, which is often represented by a symbol that is different from mu, so it is often represented by x bar, and even though the symbol changes, the entire way we calculate it remains the same. Now we are considering just small n number of population, so n is rather a subset of the capital N. Okay, it's a sample of the capital N. So what we have is, we are measuring the summing up all the lattice parameter or all the quantities are assumed by this subset of sample n population and dividing it by the corresponding population. So this is estimated mean, and it is also similarly possible for us to calculate the estimated variance. In case of estimated variance, there is a critical change that is made to the expression. Again, the numerator, it still remains the same. We have the summation ranging from 1 to small n, which encompasses the entire population, and we are taking the difference between the lattice parameter assumed by the individual alloys to that of the estimated mean. So here we are using the entire mean or the actual population mean, but here we are using estimated mean. We are calculating the estimated variance, or in the numerator the expression more or less remains the same. But in the denominator, what we have is an n minus 1. So instead of having n in the denominator, we have n minus 1. So these are the expressions to calculate the population mean and population variance, estimated mean and estimated variance. Again, the key difference here is the size of the data set that we are handling. In real life situation, what we are usually calculating is not the population mean or the population variance, but the estimated mean and the estimated variance, particularly when the your data set emerges from experimental studies or computationally expensive simulations. Then what you will essentially have is rather a restricted number of data points. At that time, what you are estimating would be estimated mean and the estimated variance. Now, the reason we have n minus 1 is rather it's rather interesting for us to understand. It plays a wonderful role, even though it appears to be rather simple. It plays a huge role. The reason why we have n minus 1 is because as your n increases and it gets close to 0, as your n, that is the size of the sample, increases and it gets close to the entire population, the entire possible population, that is the capital N, what ideally we would expect is the estimated mean or estimated variance and the difference between the estimated variance and the population variance, either way, should be equal to 0. Again, as your size of the sample increases and as it gets close to the entire population, then what ideally we would expect is the estimated variance and the estimated or the population variance should be equal to one another, or the difference between them should be negligible, and this is rather achieved by the denominator n minus 1. Now what essentially we have in the denominator is the influence of population on the estimated variable is captured by this formulation of the denominator. That is, as the sample population increases and gets close to the actual population, the difference in the variance, that is estimated variance and the population variance, it should progressively decrease and it should be close to 0, and that criteria or that aspect is captured by having n minus 1 in the denominator. And when you consider the relation between the estimated variance and the estimated or the population mean, since the denominator is rather one reduced the actual population and the size is rather reduced, so this condition is also satisfied. So that is, since already we have a reduced sample size, so therefore in addition to that, we are removing one of the member from the actual sample size. This condition is rather automatically being fulfilled. In addition to that, the critical criteria that needs to be addressed is with increase in the sample size, the difference in the estimated variance, and also the population variance should decrease and ultimately reach close to 0, a value close to 0, and that is also being captured by this n-1 in the denominator of the expression. So we have, even though described or estimated the mean and the variance, we have seen that there are two types of mean and the variance, population and the estimated mean and the variance. Often what we are calculating is the estimated mean and the variance. Now it is also possible for us, apart from, so even though the understanding of the mean and the variance, and when you look closely all these estimations about the mean and the variance, we are not calculating this mean and the variance from the PDF. That is, we are not calculating it from the function, but we are calculating it from the population and the number of the population. So the values assumed by the population and the total number of the population. So all these estimations of the mean and the variance, both population mean and the variance and the estimated mean and the variance, when you consider or look closely at these expressions that we have looked into, the way we are estimating it is by considering the values assumed by the population or the sample and the number of or the sample size that we have or the population size that we have. What we are not doing is, even after introducing the probability density function and the cumulative density function, we are not estimating these characteristic features like mean and the variance using these different functions. We are not using the PDF to estimate the mean and the variance. Now if we are able to estimate the mean and the variance using PDF, which is nothing but a function, then what it means is that we can calculate the mean and the variance of any distribution. Let me repeat, the mean and the variance are the characteristic features of the normal distribution, and so far the mean and the variance we were able to calculate it based on the population and the values assumed by the population, the quantity of the population and also the size of the population. Now we have introduced the functions to describe these distributions. Now if it is possible, if it becomes possible for us to describe the mean and the variance using this probability density function, then what it essentially means is we can use that expression to also calculate the mean and the variance for any distribution, even though we are starting off from the normal distribution. And since now we are estimating the mean and the variance using the function or any feature of the normal distribution, we are just treating the normal distribution as a function, and based on the function, since we are estimating the mean and the variance, since we also have we have also seen different functions that describe a different distribution, we can use the same approach to estimate the mean and the variance of the other functions. So the mean and the variance are no longer confined to the normal distribution, because now we are estimating the mean and the variance using a function, and we have seen there is a function for every distribution that is possible. So when you have a distribution and that distribution can be expressed in the form of a function, then it is possible for us to estimate the mean and the variance for that function if we are able to estimate the mean and the variance for this normal, for the PDF of the normal distribution. Now the mean that we estimate using a function, now when you are calculating the mean using a function, you no longer have to be worried about the size of the population. The mean that you are estimating is a population mean, and the mean that you are estimating using the probability density function is of the form. It can be estimated through this expression, through this integration that ranges from minus infinity to plus infinity. So x f of x dx. So this expression can be adopted to estimate. So here the f of x can also be the p of x, that is the probability density function that describes the distribution of the probabilities. So what essentially we have is we are estimating the mean using this expression here, and that ranges from minus infinity to plus infinity. Now this function here, it can be any function. So this can be for normal distribution, this can be for exponential distribution, and it can be for gamma distribution or any other distribution that lay in between, that do not share the features of these three rather well-known distributions. So any function can be substituted here, and for that function a mean can be estimated. And the same way the variance can also be estimated using a similar integration, wherein we are still integrating between minus infinity to plus infinity, And here what essentially we are considering is the variation or the variance and with respect to the functions that we have. So here we have included the quantities itself, and here we are considering the difference between the mean that we have calculated and the difference between the quantity and the whole square of it. And when you solve these two expressions here, you will be able to rather estimate the mean and the variance of any given function. So we have started off with the normal distribution and there's different forms of distribution. We have arrived at their different functions, and now it is possible for us to calculate the mean and the variance not only for the normal distribution, for also for the other distributions as well. Provided you are able to extract a probability density functions for that distribution, you are able to represent the distribution as a function, then it becomes possible for us to estimate the mean and the variance of any given function. Now, all these discussions so far have been rather restricted to the single independent variable. Now, often in our real life situation, we rarely focus on a single independent variable, we consider more than one independent variables. Now, let us expand our focus and try to understand how statistically, again, in the using basic statistics, basic understanding of whatever we have learned so far, how we can understand when our study includes more than one independent variable. So let us expand our studies to understanding not only just one independent variable but two different independent variables. Now, the premise of our study remains the same. What essentially we are having is we are having a set of alloys, and we are measuring initially we measured the lattice parameter of these individual alloys, and now we are attempting to measure, along with the lattice parameters, we are attempting to measure the molar volume of this alloys. So it's just two independent parameters, independent variables that we are measuring. One is the lattice parameters and the molar volume. So this is just some example or some quantities that are relevant to the material sources. So that's the reason why I have I'm using these different independent variables. These variables can be anything. You can have lattice parameter and electric conductivity, heat conductivity, lattice parameter, and heat conductivity and electric conductivity, so on and so forth. You can have any combination of variables, but the key thing is these are two independent variables. And for the alloys that we are studying, we don't know what is the relation between these two. So we don't know if both these are rather dependent on one another, or if one motivates the other or one influences the other. We have absolutely no clue. So what essentially we are doing is we are considering each and every alloy of a set of n alloys, and we are just measuring the lattice parameter and the molar volume. Now, supposing we have say 6 different alloys, and we are representing it in the form of or using a scale. We are using a scale that we have considered earlier, and for the lattice parameter, and we are considering these 6 different alloys. So the first alloy, it assumes a value here. So alloy 1, it assumes a value here, and there is another alloy that rather assumes a value. So this is for the lattice parameter. The first alloy, it assumes a value here. The value of the first alloy in the lattice parameter scale can be plotted here. The value of the next alloy, the lattice parameter scale, can be plotted here, and the value of the third alloy in the lattice parameter scale can be plotted here, and the value of the fourth alloy here, and the value of the fifth alloy somewhere here. Now, we are also estimating the molar volume for all these 5 different alloys. We are estimating the molar volume for all the 5 different alloys. So these molar volumes of these 5 different alloys, we are plotting it in the similar scale, but this similar scale is aligned perpendicular to the original scale that we have considered for the lattice parameter. So what essentially we are doing is, similar to the previous case, we have the lattice parameter scale, and on the lattice parameter scale, based on the values assumed by the alloys, we are placing the alloys. So the black one assumes the least value, so it is positioned here. The red one has a magnitude of lattice parameter greater than the black one, so it's placed here. The green one greater ones than these two, placed here, and the blue has a value greater than these 3, placed here, and so gray as the maximum value, placed here. Now we are estimating the molar volumes of each of these 5 different alloys, and depending on the volume assumed by each of these alloys, we are placing it on the horizontal scale. So you can assume it to be a scale similar to the lattice parameter, and once you have placed your alloys and placed your alloys on the scale, you are rather tilting it and making it perpendicular to the lattice parameter. That is one way of assuming it. The other way of assuming it is rather you are considering it as a scale that is vertically placed as opposed to the horizontal scale, and now we are placing the molar volume assumed by these different alloys. Now what you observe is the molar volume assumed by the black alloy assumes a position here. The molar volume assumed by the blue alloy, it assumes a position here. The molar volume assumed by the red alloy, it assumes a position here. The molar volume that is assumed by the green alloy, it assumes a position here. And the molar volume that is assumed by the gray alloy, it assumes a position here. So similar to how you have placed your lattice parameter, you are placing the molar volume assumed by the different alloys on a scale, but that is the scale is rather perpendicular to that of the scale of the lattice parameters. Now when you are placing these alloys, you are considering the individual independent variables of each of these alloys. So when you are placing these alloys on the lattice parameter scale, we are considering each alloys individually and each of these independent variables individually. In the same way, when you are considering the arrangement of the alloys in this axis, what essentially you are doing is you are considering the individual values assumed by each of these alloys and then placing it here. Now when you represent these scales, or when you place these scales in a perpendicular manner, what you establish is you establish a space that allows us to represent or consider or treat these independent variables as a pair. So when you place or when you consider these scales in a perpendicular manner, when you have a perpendicular representation of a scale, what you essentially having is you are creating a space that reflects as Cartesian space and that allow us to rather relate or understand or study instead of these individual values, instead of these individual independent parameters, it allows us to rather treat these two independent parameters in this given space. Now this space allows us to treat these two independent parameters together as a pair. Now when I do that, it is possible for us to treat these two independent parameters pertaining to the black alloy, and the corresponding, when I rather treat these as a pair, the corresponding value will assume a position here. So for the alloy represented by using the black color, when I treat the independent variables as a pair, the corresponding position will be here. So I just have to have this corresponding position here. Now in the same way, when I treat the independent variables of a given alloy as a pair or together, the corresponding position in this space will be here. And the same way, it is possible for us to treat the independent variables as a couple, and it will lead us to this point here. And for the alloys represented by blue, it is here, and for the alloy represented by gray, it is here. So what essentially we have done is we have treated the independent variables of the different alloys as not as individual but as pairs. We have treated us as an individual while we are dealing with a single scale. Now we are dealing with two different scales, each associated with a given independent variable, and we have placed the scale is in such a way that they represent a Cartesian space. And now once we have introduced the Cartesian space, what essentially now we are doing is this space will allow us to treat the independent variables as a pair, and when we are treating these independent variables as a pair, they provide a unique representation of these independent variables in the space. We are representing these independent variables as a pair in the space. So each of these points, they represent a specific alloy. So like in the individual scales, each of these points represent a specific alloy. Here each of these points, they represent a specific alloy. Now it is possible for us to observe rather a relation between in these different points that we have considered. So each of these points represent not just one independent variable, but they represent two independent variables, and each of these points, they represent the members of the population, the sample that we have considered. And what we essentially observe in these numbers is there appears to be some sort of a relation, and this relation is what we will be able to qualitatively describe using covariance. So what covariance allows us to do is, the covariance allows us to find out if there is any relation between the two independent variables that we are studying for a given population of, say in this case, an alloy. So we are studying a population of alloys and we are estimating two independent variables. We don't know much about if these variables are related to one another. We don't have any clue about it. But what we are doing is we are treating the two independent variables in a space that we have created by projecting or by having these scales perpendicular to one another. And then we are treating the independent variables of each of these alloys as a pair, and when we do that, we observe a relation that exists between these alloys, and these are rather described using covariance. So whenever you have a population that describes a set of independent variables, when you say that there is a covariance associated with it, with this set of population, what you essentially means is that there is rather a relation that exists between these alloys or this population. Again, you are considering a population, and in that population you are considering two different independent variables, and in that context, when you say there is a covariance that exists between this amongst these population, what essentially you mean by that is there is a observable relation that exists amongst this population. Now in this case, it is possible for us to rather express or qualitatively show the relation that exists among these population. When you draw a straight line, what essentially you observe is there is this relation, this trend. The other way of referring to this relation is the trend. You are able to observe there is a trend that exists in this population, and this trend is rather can be expressed qualitatively by introducing a straight line. And since this straight line has a positive slope associated with it, so initially you are identifying, you are visualizing a relation, you refer to it as a trend, and this relation you are able to rather qualitatively capture by introducing a straight line, and this straight line has a positive slope, and therefore the covariance that we observe is rather a positive covariance. So we have considered, again getting back to our premise, we have considered a population of alloys, and we are considering, instead of just estimating one independent variable, we have estimated two independent variables, molar volume and the lattice parameter. And when we plot these two independent variables in a space, and when we handle these two independent variables not individually but as a pair, it becomes possible for us to represent these independent variables in a space that is created by the scales that are arranged perpendicular to one another. And each of these points, they no longer represent an individual. In addition to representing these individual lattice parameters, they also are representing the alloys in our case, the members in our entire population. And now what we observe is there is a relation that exists between these members, particularly in terms of these different independent variables that we have considered. So there is a relation that exists between the different independent variables. There is a trend that we observe in the different independent variables for the population that we have considered, and this is rather can be qualitatively expressed by the covariance. All we need to do is we need to describe this relation using a straight line, and when you have a positive slope, what we end up having is a positive covariance. Now if we reverse the situation, if it is also possible for us to measure two different independent variables. For instance, it is possible for us to measure, say, our density and lattice parameter. So when we measure density and lattice parameter, again similar to that representation, what we are doing is we are creating a space perpendicular to one another. So what essentially we have is the lattice parameter along the x-axis and the density along the per se we cannot use the term x and y axis, but you have the lattice parameter as the horizontal scale and the density as the vertical scale. It is possible for us to observe a variance of this form. It is possible for us to observe the trend that is of this form here. So what essentially we are observing is that, as opposed to the trend that you see when you are comparing two different independent variables, that is molar volume and lattice parameter, you see a trend. You are able to observe there is a relation between these two variables for the given population. There is a relation between these two variables for the given population. But when you want to rather qualitatively describe this relation, when you rather introduce a straight line to describe this relation, what you observe is the slope of the line that qualitatively describes this relation or the trend is rather negative. So therefore, what we essentially observe is a negative covariance. So we are considering two different independent variables, and these two different independent variables, we are treating it as a pair, and they are representing it in a space, and this space is rather constituted by the scales that are perpendicular to one another. And just by this representation, we are able to observe a relation, and qualitatively we are describing this relation by imposing a straight line. When the slope of the straight line is positive, we refer to it as the positive covariance. When the slope of the line is negative, we refer to it as the negative covariance. We have not quantified anything as of yet. We have just provided some representation of the two independent variables, and these representation themselves reveal that these two independent variables are rather they exhibit a trend. They are related to one another, and we are rather describing these independent variables or these relations, this trend using a straight line, and depending on, in a simplistic way, qualitatively using a straight line. And of course there are deviations, all these points do not go through the straight lines, but we are just representing it using a straight line. And when we do that, depending on the slope of the straight line, we are able to state if the relation that we observe. So we are able to express this trend or the relation using the covariance. We refer to it as the positive covariance or the negative covariance. Now it is also possible for us to have, say for instance, we are considering the lattice parameter and the diffusivity of your sample as the two independent variables. It is possible for us to have such, when you represent these two variables for the different alloys that you consider, it is possible for us to have such arrangement of these individual points or the individual alloys in the space that we have created. So as opposed to what we have seen in these two representation, it is possible for us to have such a distribution of these 2 points in the space that we have created. Now when you try to rather observe any trend, no trend is rather visible, and when you try to fit a line or when you try to qualitatively capture the trend that is non-existent, what you end up having would be a straight line, and this means that there is no relation or trend that exists marks these population for the variables that we have considered. So that means there is no covariance that is associated with these two different variables for the population that we have considered. So essentially what we have observed is we have moved away from a single independent variable to two independent variables. We have seen how it is possible for us to observe if there is a relation or trend between these independent variables, and graphically we are able to observe this trend, and when we want to describe that, we use the term covariance. The covariance can be of 3 types. One is positive covariance, and the other is negative covariance, and the other is zero covariance. These covariance, positive, negative, they are rather associated with the slope of the line that we use to rather capture the different the trend that we observe in these 3 different or the 3 different relations, or the trend that we see for the combination of the independent variables. Now, even though this conceptual understanding of covariance is sufficient, there is a reason why we refer to this as the covariance, and the reason is because the position of these individual points that we are considering. So these are, so we will go back to this elementary representation of how we came about with this rather representation of the individual alloys. Now when you consider these points, these individual points, what they indicate is, what they capture is these points, that is these points in the space, they are indicative of the position of the independent variables away from the mean. So this point here is representative of the position. So this point here is representative of the position of the independent variables in this axis and in this axis. And when you consider the position of this independent variables in this axis and in this axis, they are away from the mean. So when you want to quantify their rather separation from the mean, the way you would estimate it is through variance. But here we have the variance of 2 independent variables, and the variance of these 2 independent variables is what gives you this point here. So we have two variance of these two independent variables, and that is what is being captured here. And the same way the variance of these two independent variables is captured here, the variance of these two independent variables is captured here, so on and so forth. So each of these points is nothing but the variance of these two independent variables, and that is captured in the space. So how much away are they from the mean is what being captured by each of these points in the scale, and the combination of these points in the scale will give you the point in the space. So essentially then what we are doing is each of these points in the space is nothing but the representation of the variance of each of these points in the scale. Now when we say we observe a trend, what we are observing is a trend in the variance of each of these points in both these scales. So we observe a trend in each of these points. When we say there is a trend in each of these points that have been captured in the space, when we say there is a trend in each of these points captured in the space, what we are essentially saying is there is a trend in the variance of these parameters that we have considered in the horizontal and the vertical scale. So each of these points, the position of these points in the space that we have created, the two-dimensional space that we have created by placing the variables horizontally and vertically. So the position of these points, they are dependent on the variance. So variance meaning how much far away are they from the mean. And now when we say that each of these points they exhibit a relation with one another, they exhibit a trend with one another, what essentially we are saying is there exists a relation between the variance of each of these points. So therefore, since the relation that we observe is rather reflective of the relation that we observe in the variance of each of these points, so what essentially therefore this is rather meaningfully referred to it as the covariance. So this is just a justification for why we refer to this relation as the covariance. So essentially each and every point in a given space is the position of it depends on the variance, how much it is away from the mean. And when you see that there exists a relation between all these points that are captured in the space, what essentially we mean is there exists a relation between the variance of each of these points. And this variance it is for two different independent variables. And now since this particular relation captures the variance of these two different the variance of the different points, it captures a relation between the variance of these different points, or this relation, the trend that we observe is due to the variance of these different points, we refer to it as the covariance. And now with this understanding, with this conceptual understanding of why we refer to this trend as the covariance, it is possible for us to rather from this understanding, when we consider the expression for the covariance, it becomes even more a bit more comprehensive. So the covariance is expressed when you consider the numerical expression for the covariance, it is expressed of this form. When you consider the entire population that ranges from 1 to n, so the covariance for it is expressed as x minus mu x to x minus mu, or rather y minus mu y divided by the n. So this is the expression for the covariance of the set of points that we have considered and that exhibits a trend. So you have a set of points that exhibits a trend, and that trend, if you want to qualitatively express it, you introduce a line, and based on the slope of the line you can either call it as a positive covariance or the negative covariance. And if the line is rather straight without any, or completely horizontal without any slope, you say that there is no covariance that exists between these variables. And when you want to quantify this covariance, and having understood why we refer to it as the covariance, then it becomes possible for us to understand this expression that quantifies this covariance. What we are considering is x minus mu x is nothing but the position, or how much these x's are away from the mean, and y minus mu y is so how much each of these points are away from the mean, and y minus mu y is how much each of these points are away from the mean y, and we are taking the ratio with respect to the entire population. Now when you want to have, instead of the population covariance, when you want to, so for the sample size that we have right now is just 5, so in that case what we have is just a smaller sample of the entire population, and correspondingly the expression for the population mean, the symbol for the population mean, or the population mean, should be replaced by the estimated mean, and when we do that we end up with this expression here. So the covariance For the population is expressed in this manner. The covariance for a sample of size much smaller than the entire population, n, is expressed in this manner. So these are the two expressions that help us quantify the covariance. Now, before winding up this discussion on the covariance, if you consider this particular trend, if you want to make sense out of how the slope of the covariance, how the slope of this line would help us understand, would relate to rather the magnitude of the covariance. For instance, here what we have is a negative slope, and if I estimate the exact value of the covariance for this particular combination of independent variables, then that value should also be negative. So if we want to estimate, if we want to cross check, will the slope of the line that I have introduced to qualitatively represent the covariance, will it coincide, will the sign of that line will rather be recovered by the population? It is possible for us to do so once we are able to introduce the corresponding mean. Let me repeat. So far we have said that there are three different types of covariance: positive, negative and zero. And now we have arrived at an expression to rather quantify the covariance. So when you quantify the covariance, it is possible for us to have a positive value, negative value or a zero value. Now when I have the positive value, then the slope that I get for the line that I have graphically introduced should also be positive. In this case, if I have already fitted or I have already introduced a line and slope of that line is negative, so for this, when I estimate the or quantify the covariance, it should also be negative. Now let us try to find out. So just for a few points, let us try to find out if this works. Now when you consider the mean of this curve, so let us consider rather a simplistic representation like this, and our points are these. So these are our points, or let us make it a bit more easier. So these are our points. And now it is possible for us to consider the mean of the x-axis and the mean of the y-axis. So now when we consider this particular trend here, now this is the mean of the y-axis and this is the mean of the x-axis, and this is y1 and this is y2, and similarly we will have x1 and x2. Now when you consider the overall trend, this will be a negative trend. So the overall trend will be negative. So we already know that this trend is negative. From the graphical representation itself, we know that what we have is a negative covariance. Now let us try to find out if I quantify the covariance, if the value that we get will be negative. So when I do that, what we end up having is this value here for this set of sample. When I consider my difference, that is y minus or y1 minus y and y2 minus y, what I would end up having is y1 minus y and y2 minus y. These two values will be positive. And now when I consider x1 minus x and x2, that is the difference between these two and the difference between these two, again in keeping with the formula. So that is y1 minus y and y2 minus y will be this part of the expression to quantify the covariance. x1 minus x and x2 minus x will be this part of my expression to quantify the covariance. So these two will be negative. So in this quadrant, when I consider this quadrant, the variance of the standard deviation of x and its corresponding mean will be negative, and in the same quadrants the difference between yn and yi and y would be positive. So essentially when I take the product of these two, then in this quadrant I would have the values, the covariant values that are negative. Now when I consider this quadrant here, what I have is, say for instance here, for these 2 points here, what I have is the x3 and x4, and similarly y3 and y4. Now when I consider the difference between my y values, that is y3 minus y and y4 minus y, they lie below the mean of the y independent variable, so therefore they will be negative. And when I consider x3 minus x and x4 minus x, they are beyond the mean of the x-axis, that is x3 and x4, so they will be positive, and the combination of these two will give me again a negative. So the combination of these two will give me a negative value, the combination of these two will give me a positive value. So in these quadrants, the x values, the difference in the x will give me the negative values. In these quadrants, the difference in the y will give me the negative quadrant, but cumulatively what I end up having is a negative slope. So therefore, despite having the expression for the covariance, what ultimately we have ended up having is rather the we are able to recover rather the trend in the distribution of these data points. So despite quantifying the covariance, we are able to recover the same trend that we would have observed through the graphical representation itself. So the covariance, it quantifies the expression, it quantifies the covariance, but the trend still remains the same. So here we are able to recover the negative trend through the quantifying the covariance that exists between these different points. So with this, we will wind today's lecture up, and in the subsequent lecture, possibly the last lecture, we will wind the discussion up with what we refer to it as the correlation. We will so far this has been just a qualitative representation of the trend. We will make it more quantitative, more specific in the subsequent lecture through correlation. Goodbye.